These are the notes for AP Calculus on the topic of solving differential equations by separation of variables. So a differential equation is any equation that has a derivative in it. And in this case, the ones we're going to look at are fairly simple to be able to see. They just start out with the derivative looking like this, dy dx. Well, that could be other variables as well. And the method is called separation of variables because that's what you have to do first. So here's the steps we're going to be taking in these problems to find what's called the particular solution of the differential equation. So what we're doing is we're going to be starting with the derivative and getting back to the original equation that has this derivative. And when it says particular solution, that means we're going to be able to solve for that plus c you get when you evaluate indefinite integrals. We're going to have some information that helps us figure out that constant. It'll be a particular solution rather than a general solution is when you don't know what that constant is. So the first step is going to be to separate the variables. And the main operations you're going to be using are either multiplication or division. So that each side of the equation contains only one variable. Right? So before you can do anything else, you have to separate the variables correctly first. Then, once they're separated, then you can integrate and find the antiderivative of both sides of the equation by integration. And then what we'll do is find the value of the constant c to get our particular solution by substituting the initial condition. And finally, we're going to solve the differential equation for the variable that appears on the numerator of the derivative of the differential equation. That should be all in there. Okay, so this one says find the particular solution y equals f of x to the given differential equation with the initial condition f of 1 equals -2. Okay, so we're trying to find the particular solution again. That's the original equation that has this derivative. And this tells you it's a function, and the initial condition we're given that has to be on that function is 1, -2. 1 is -2. So the first thing we do to separate the variables is to separate the dy from the dx. One way to do that is just multiply both sides of the equation by dx. So when we do that, we'll get the dx's will reduce out there, and we'll just be left with dy equals y cubed x minus 2 dx. But the variables are not separated now because although the x is with the dx on the right side, notice there's also a y on the right side. Now y cubed needs to be over here with the dy to have them separate correctly. So the way you can get it over there mathematically is to divide both sides of the equation by y cubed. But remember, the next step, rather than writing this side as dy over y cubed, the next step is going to be to find the antiderivative or integrate it. So rather than writing it as 1 over y cubed, that's the same as y to the -3. That's dy equals, on this side now all will be left is x minus 2 dx. So now you can see that y is with a dy, the x is with a dx. Now we have the variables separated correctly. And as soon as they are, then your next step is to integrate both sides to find the antiderivative. So when you integrate or find the antiderivative of y to the -3, you get y, you add 1 to the exponent, y to the -2 divided by -2 using the power rule for integration. And on the right side, since these are subtracted, you can just integrate each one separately. So you integrate x, you get x squared over 2. Integrate the constant of 2, you just get multiplied by the variable x. And if you integrate these, you might think, well, they both should have a plus c, some unknown constant on both sides. But really, to make it simpler, we don't need 2 unknown constants. You could always add or subtract this constant over and combine it with the constant on this side. So we really only need 1 unknown constant plus c. And I put it on the right side, not because it has to be there, but because it's easier if we put it over there. Because remember, what we're going to do is eventually solve this for the variable that's on the numerator, which is the y. So you might as well put the plus c over there. Will be one less step when you're trying to isolate the y. So next, after you find the answer and integrate both sides, let's make it as simple as possible to work with. So the right side's simplified all the way, but the left side we got that negative exponent, so let's go ahead and rewrite that. It's the same as 1 over -2y squared. Just bring that y to the -2 down in the denominator, equals x squared over 2 minus 2x plus 3. So that's what's called the general solution. But because we're given this initial condition, that's a point on the original function, this is saying when x is 1, the y coordinate is -2, so that corresponds to point 1, -2. And we can use that by substituting that in to our general solution for x and y, and that allows us to solve for that constant c. So we substitute in 1 for x and -2 for y. So this will be 1 over -2 times y is -2 squared equals, we'll substitute in 1 for x, so 1 squared over 2 minus 2 times 1 plus c. And we can start to simplify this. So this -2 squared is 4 times -2 is -8, so you have 1 over -8, or -1/8, equals 1 squared, that's just 1, so you have 1/2 minus 2 times 1, 2, plus c. And let's just move it over here so we can keep simplifying here. So if we combine the terms on the right side, -1/8 equals 1/2 minus 2, that's like subtracting 4/2, gives you -3/2 plus c. And then all you have to do to solve for c is add 3/2. But since this is a fraction, we want to get a common denominator, and adding 3/2 is the same as adding, if you multiply 2 times 4, that's 8, so 3 times 4 is adding 12/8. So c then would equal 12/8 minus 1/8, 12/8. So now we know what that constant is. So now we can substitute that right back in here for c. So now what we have left here is 1 over -2y squared equals x squared over 2 minus 2x, and we just figured out c is 11/8, so plus 11/8. And now the last thing we have to do is to make this a function, y equals f of x, it has to be solved for the variable that's on the numerator. So we want to isolate the y. So to isolate the y, there's different ways to go about it, but first it's probably easiest if you get rid of that -2 first by multiplying this entire equation by -2. So that'll reduce the -2 there, so you'll just be left with 1 over y squared equals, when you multiply -2 times x squared over 2, the 2's reduced, but you're just left with negative and the x squared, so -x squared. -2 times -2x is positive 4x. And -2 times 11/8, well, that's going to be negative. And the 2 goes into the 8, reduces that to 4, so it would be a -11/4. Now, that y squared is still in the denominator. So next what you can do, similar to like we did with the -2, is multiply both sides by y squared. I'm going to write it a little bit differently here. Here we're going to multiply this side by y squared to get the y squared to reduce out. But unlike what we do with the -2, we don't want to distribute the y squared times these, because that'll make it more difficult to solve for. Instead, I'm just going to put parentheses around that, and then times y squared. So that way on the right side, you can see those y squareds will reduce out and just be left with 1 equals -x squared plus 4x minus 11/4 times y squared. That way, our next step to help us isolate the y squared, now it's not on the denominator anymore. Now we can just divide by this -x squared plus 4x minus 11/4. And you can balance it out, divide the other side as well. So now, if we just switch the sides around, we'll have y squared equals 1 over -x squared plus 4x minus 11/4. Now, to isolate the y, the next thing you do is you take the square root of both sides. So now we just have y equals, but we've already taken even root of both sides. Remember the first thing you need to add in front is plus or minus. Now you could leave it just like that, but the numerator, we know the square root of 1 is just 1, so we can just write that as 1 over, and then the denominator we would just leave inside the radical. Square root of -x squared plus 4x minus 11/4. And you might think, well, that's it. We got isolated the y. There's our answer for the particular solution. However, there's one problem with that. Remember, it says this particular solution y equals fx, that means it's a function. And remember the definition of a function is, if you substitute one independent variable, in this case x, you're supposed to only get one dependent variable y out. But look at our function right here, or our equation right here. If we substitute a single value for x, notice we're actually going to get two different y values because of that plus or minus. So if you leave it like that, that's not a function. So the way to tell which one it is, because it can't be both, you keep it a function, it's either got to be the plus or the minus, is to look at your initial condition. If you look back here, look at the y coordinate we had right here. It was a negative y coordinate. So notice the only way this is going to be a negative y coordinate is if there's a minus out front. Because the principal root here is always going to be positive, and this 1 is positive. So that's what indicates that it would have to be the negative. Now if this had been a positive y coordinate as our initial condition, then we would know it would have to be the plus rather than the minus. So that's how you can determine on this type of problem which one it is. So your final answer for the particular solution would be y equals negative 1 over the square root of negative x squared plus 4x minus 1. All right, let's take a look at another example. This one, again, we're looking for the particular solution. So we're going to solve it for the variable on top of the y, and it's a function again. And this time, for this given differential equation, because it has a derivative in it, with the initial condition f of 3 is 2. So this time, that means the point 3,2 is on our function. So sometimes you have a derivative that's a fraction. And when you do, like this one, rather than just multiplying both sides by dx, which you could do, it's probably easier to just cross multiply when you have a fraction equal to a fraction. And remember, that means you multiply the numerator of this fraction by the denominator of this fraction and set it equal to the denominator of this fraction times the numerator of this fraction. So since we're going to be solving for y, I usually keep the variable I'm solving for just on the left side of the equation just to be consistent. But you don't have to. So 3y squared times dy equals sine of pi x times dx. And now we can see if the variables are separated. So the y's are with the dy, the x's are with the dx, pi is just a constant, so they are separate. So this won't always separate them by cross multiplying. Sometimes you might have to do some more steps that are separated, but at least get rid of your fractions to start with. So now, once they're separated, you can integrate both sides on the antiderivative. So this side's pretty straightforward. The 3 is a constant, so that would just stay there when you integrate. And then when you integrate y squared, you get y cubed over 3 equals, but if you take a look at the right side, it's not quite as simple. It's not just sine of x, it's sine of pi x. So because there's this function inside here, we can't integrate it just like this. This is where you'd have to use u substitution. And you'd say u equal to the function inside, which is pi x. So we've still got the integral sign there. But now we can write it as the sine of u, since we said u equal to pi x. But remember, we don't want dx here, because then dx and u wouldn't match up. It would be the same variable. So the way we get rid of the dx, to replace it with a du, remember, is to take the derivative of what you said u equal to, in this case, pi x. So the derivative du dx, well, the derivative of pi x would just be pi, just like the derivative of 2x is 2, because pi is just a constant. And then if you multiply both sides by dx, you get du equals pi x, and then divide by pi, so dx equals du over pi. So we can take that and substitute it in for the dx right there. And then we can start simplifying this. So the 3's reduced out here, so we just have y cubed equals, here you can pull out the 1 over pi out in front, because that's just a constant. And now we've got just sine of u du. So a simple integral, sine of the single variable, which we can integrate. So we start with y cubed equals 1 over pi. When you integrate sine of u, that gives you negative cosine of u. So that negative would just get multiplied by the 1 over pi out in front. Because remember, when you integrate, if the answer starts with a c, which it does here on trig functions, the answer is negative, and then we need our plus unknown constant. But we're not quite done with the right side because we still have that u in there. So remember the last step on these indefinite intervals, to get rid of the u, you substitute the pi x back in there. So we have y cubed equals negative 1 over pi times the cosine of pi x and then plus c. So that's our general solution. But we don't know what this constant is yet. And then to find the particular solution, to figure out what that constant is, again, you use this point right here, with the initial condition. It gives you a point on the original function that allows you to solve for what c would have to be. So we're going to again substitute that in for x and y. So for y, we're going to substitute in 2, so that'll be 2 cubed. And for x, we're going to substitute in 3. So that'll be cosine of 3 pi. Well, 2 cubed gives you 8. And then we have negative 1 over pi times cosine of 3 pi. Well, if you draw out where 3 pi is, there's pi. If you go around the circle one more time, 3 pi is in the same place. And cosine, the coordinates at that point are negative 1, 0, and cosine is the x coordinate, so it's negative 1. And then plus c. So just move it up here. So we have 8 equals 1 over pi plus c. Last step to solve for c, just subtract the 1 over pi. So you get 8 minus 1 over pi equals c. So that's okay, because pi is just a constant. That's close to 8 minus 1/3 around there. So close to 7 2/3. But we can leave it in terms of pi to be accurate. So now we take that c value and we substitute it back in here for c. So what we have left now is y cubed equals negative 1 over pi times the cosine of pi x. And we just figured out c is 8, so plus 8 minus 1 over pi. And now, to isolate the y, you would just take the cube root of both sides. That'll give you y equals. And when you take the cube root of both sides of the equation, there's only one answer on odd roots, so you do not need a plus or minus here. So it's just the cube root of negative 1 over pi, cosine of pi x, plus 8 minus 1 over pi. All right, let's take a look at the next problem here. Now let's take a look at some, those are more abstract problems. Now let's look at some applied problems for the same process. They look a little different though because there's no x and y, we've got some different letters in here. So it says given h equals 16 at time 0, where h is the height in inches of the water in a container, and t is the time in minutes, solve this differential equation for h as a function of t. So again, notice what we're solving for is the variable on the numerator h. So the first thing we need to do is separate the variables. In this case, our variables are h and t. But be careful, when you have a negative out in front like this, if you simplify this, because notice we have a fraction equal to a fraction, so probably cross multiply will wipe out the fractions. But when you simplify that, it's probably easiest to just treat that negative as part of one of these. So I'm going to treat it to go with the 2 rather than the square of h. But either way, it's fine. Just choose one or the other, not both. So negative 2 times dh, when you cross multiply, would equal square root of h dt. However, notice we want to get the variables separate. Last problem, when we cross multiply, the variables were already separated. This time they're not. So notice the square root of h is with the dt, these are on the side. There are no t's, so we don't have to worry about moving those to the dt side. If there were, they'd have to be over here with the t. So again, we're just going to divide by the square root of h to get it on the correct side. And then remember, our next step is going to be to integrate. So let's go ahead and rewrite this as negative 2, and instead of square root of h on the denominator, that's the same as h to the 1/2, and when you move it up to the numerator, that's h to the negative 1/2 times dh equals, all that's left here is just dt. So now the variables are separated, h is with a dh, and again there's no t's, so if there were, they'd have to be over with a dt. So once they're separated, remember, then you can integrate both sides, find the antiderivative. So on this side, the negative 2 is just a constant, that just stays out in front. And then when you integrate h to the negative 1/2, using the power rule, you add 1 to the exponent. So when you add 2 halves to negative 1/2, you have positive 1/2. And rather than dividing by 1/2, that's the same as multiplying by the reciprocal of 1/2, which is 2. And on this side, well, to integrate it, it's not much there, there's just a 1 in front of it. So when you integrate a constant, it just gives you the constant times the variable, which in this case is t. So when you integrate 1, you just get t. And then, of course, we need our plus c, our unknown constant. Let's go ahead and simplify this first then. So this just becomes negative 4, and it's easier to work with in radical form, so if we write it as the square root of h equals t plus c. Now we need, that's our general solution, but we need to know the particular solution by solving for c. Notice here they write it a little differently, but they tell you a point you could use on this is right here. H equals 16 at time 0. So we can substitute that in for h and t, and that'll allow us to solve for c. So it'll be negative 4 times the square root of h, which is 16. T is 0 plus c. So square root of 16 is 4 times negative 4 is negative 16 equals c. So there's our c value. I can take that and substitute it right back in here. So now we've got negative 4 times the square root of h equals t, and we just figured out c is negative 16. So last thing we have to do, notice it even tells you here, we're solving the differential equation for h as a function of t. So we have to isolate the h, and again, that's because it's on the numerator as well as the fact that it tells us to do so. So to get h by itself, first you would divide both sides of the equation by negative 4. Here you can have a choice. You can divide it all by negative 4, or you can divide it separately. I'm just going to divide it all, but either way would work. So then you have the square root of h equals t minus 16 over negative 4. And finally, to isolate the h, you would square both sides. Get rid of the square root. So we'll have h equals, and let's see if we can make this any simpler. You could leave it like this, but t minus 16 squared, well, to square that out, you have to write t minus 16 and t minus 16 and write it twice and distribute it out. So it's probably simpler to just leave it in factored form as t minus 16 squared. But the denominator is just a constant. Negative 4 squared is just 16. So that's what they're asked to find. And look at what this tells us. Now we have a function that would give us the height. H was the height of the water in the container at any time. So if you wanted to know what the height of the water is at time 5, you would just substitute a 5 in here. And now I give you the height of the water at time 5. And if you want to know when the container became empty, you could plug in 0 for h and solve this. And you notice you substitute 0 for h and solve it. You set the numerator equals 0. You can see t equals 16 would make the numerator 0. So when this container becomes empty, it would be at time 16 minutes in this case. All right, let's take a look at one more applied problem. This one said let v of t be the velocity in feet per second of an elevator at time t seconds. The velocity of the elevator satisfies this differential equation. So, with this initial condition, v of 1 is 3 pi over 2. Find an expression for v in terms of t. So again, notice we're solving for the variable that's on top. So just think about what we actually have here. They don't use the word, but this is the derivative of velocity, right? dv dt. And what is the derivative of velocity called? That's called acceleration. So what we're really doing in this problem is we're starting, this is giving us the acceleration function, and by separating the variables and integrating, we're working back to get velocity. Remember, that's the reverse. If you had the velocity and you wanted acceleration, you would take the derivative. So now, in order to go from acceleration to velocity, that's why we have to integrate. So, since our derivative is a fraction, first thing you probably want to do is cross multiply. So that would give you cosine of v dv equals 3t minus 4 to the 6th dt. And we cross multiply the v's with the dv and the t's with the dt, so the variables are separated perfectly. And as soon as they're separated, remember that you can integrate both sides. On the left side, cosine of v, that can just be integrated. That just becomes the sine of v. But on the right side, you have a couple options. You could write this out 6 times and multiply it out, or use Pascal's triangle to figure out the pattern and write it out, but still that would take a long time. Or the easier way, since we have this function inside, is to use u substitution. And just set u equal to 3t minus 4. So that way, we still have the integral sign here, because we haven't integrated this side yet. Now we can just write it as u to the 6th, which is a lot simpler. But we still need to replace the dt with du, so the way we do that again is to take the derivative of what you said u equal to. So du dt, derivative 3t minus 4 is just 3, and then solve that for dt, multiply both sides by dt, gives you du equals 3 dt, and then divide by 3, so dt equals du over 3. Let's substitute that right in here. So you have the sine of v equals, you can pull out the constant of 1/3 out in front, and then all that's left is u to the 6th. So now we turn a more complicated into a simple one we can actually integrate. So we have the sine of v equals the 1/3 constant just stays out in front. And then when you integrate u to the 6th, you're using the power rule for integration, you get u to the 7th over 7, and then plus our unknown constant c. But we're not quite done with the right side because remember, on these indefinite intervals, we want our answer back in terms of the original variable, which was t. So you can take this 3t minus 4 and substitute back in for u. So I have the sine of v equals, and we can go ahead and simplify this at the same time. That's going to be 3t minus 4 to the 7th over 21, and then plus c. Alright, so that's our general solution, but we're also given the initial condition v of 1 is 3 pi over 2. So, to figure out which variable is which one's like x and which one's like y, what we normally have, well, here, notice this is v of t, so you can see t represents the number that's inside there. And notice t is on the denominator where the x usually is when we have dy dx. So that should include t is the independent variable. So that's going to be like your x, and v is where the y usually is, so that's like your y. So tv. We get our points. So in this case, the point we have is 1, and time 1, the velocity is 3 pi over 2. So we can substitute that in there for t and for v. So that becomes the sine of v, which is 3 pi over 2, equals, plug in 1 for t, so that'd be 3 times 1 minus 4 to the 7th over 21, and then plus c. And then we can simplify it. The sine of 3 pi over 2, well, 3 pi over 2 is right here, and the sine is the y-coordinate, so that's negative 1. And it simplifies, let's see, 3 times 1 is 3, minus 4 is negative 1 to the 7th, it's an odd exponent. So that'd be negative 1 over 21 plus c. And then to solve for c, we just add 1 over 21, both sides. So c would equal, well, negative 1 is like negative 21 over 21. Plus 1 over 21 gives you negative 20 over 21. So that's what you can substitute back in for c there. We've almost got our answer. We've got the sine of v equals 3t minus 4 to the 7th over 21, and we just figured out c is negative 20 over 21. And now we just have to isolate the v expression for v in terms of t. We'll get the v by itself. Notice that's the variable that's on the numerator. That's the one you always isolate. So then, since the v is stuck inside of the sine, the only way to isolate it is to use the inverse of sine, which is called arc sine. Sometimes you'll see it written like this, like on your calculator. But here, I'm just going to write it as the arc sine. So we're going to take the arc sine of the sine, and that means we're going to take the arc sine of the other side of the equation as well. So we took the arc sine of both sides of the equation, and what that accomplishes is because sine and arc sine are inverses, they reverse each other and cancel out. We're just left with v. In other words, the sine of 3 pi over 2 is negative 1, right? But the arc sine of negative 1 would give you back 3 pi over 2. It reverses it. So you're back where you started with, so we end up with just v, which we're trying to solve for. And you could leave it like this, or because they already have a common denominator, you might want to just combine it to be a single fraction. Might look a little simpler, as just 3t minus 4 to the 7th minus 20, all divided by 20. And that concludes the notes for AP Calculus on the topic of solving differential equations by separation of variables.